All right, so today's discussion is going to be on stereochemistry. Now, stereochemistry is essentially um, viewing organic chemistry in three dimensions. And so we, in the past, have introduced constitutional isomers. And we have to remember that constitutional isomers differ in the bond connectivity. So there's different bond connections there. And they're going to have the same molecular formula, again, just different bond connectivity. Now, we also introduced stereoisomers already. Stereoisomers that we've seen already were going to be the cycloalkanes that have cis or trans substituents on them. We also have seen alkenes that are cis or trans. And the idea of stereoisomers is that they differ in the three-dimensional orientation of that molecule. So that's what, for example, the cis or trans cycloalkane. We would have a methyl poking out at us and a methyl poking away from us. And so those are going to give since they differ in the three-dimensional orientation, they're definitely going to have a different IUPAC name. But it's only going to differ slightly, whereas constitutional isomers, it differs completely because it's different bond connectivity. But then, in addition to the slightly different name, we may or may not have a very different reactivity, and so it's going to affect the physical properties as well as the chemical properties of that particular molecule. Now, a perfect example, which we are all, I'm sure, aware of, is the difference between sugars, right? And so we have here amylose, or it's one form of starch. We have amylose and amylopectin. Starch, that's your yummy bread and your wheat and your sugars, essentially. Whereas cellulose is like cotton or just different portions of the plant that our bodies can't digest. Now, notice the structure, the bonding of these two positions for the oxygens that I've circled. They're just structurally different in terms of their three-dimensional orientation. Now, the OH group can be axial or equatorial, and that's essentially what's going to create that different three-dimensional orientation. But also, what's really important is that they both consist of glucose molecules. They're glucose polymers, and what happens because of that different bond connectivity at that oxygen is we get a different three-dimensional, like a macromolecule. So the cellulose is looking kind of flat right there, while the starch is cylindrical, or it's kind of like forms like a helix, right? Now, why am I mentioning this? It's because even though they consist of glucose, the same molecule, the same sugar, our body digests starch very well, but not cellulose. And so their three-dimensional structure essentially affects the ability for us to digest this, which is essentially a chemical reaction. And so I'm just pointing out the importance of the chirality or stereogenic center or stereochemistry in something that we are already familiar with. Okay. All right. So another thing that we want to talk about is something we're super familiar with, and hopefully we're washing quite a bit, is our hands. And before we get into the discussion of our hands and our obviously feet, we want to bring up the term chirality. So I mentioned it before. Now, what is chirality? So chirality has to do with stereochemistry, of course, and our hands are a perfect example. We have our left and our right hand. This is a mirror right here, and you can see that our left and right hand are mirror images of one another. And the cool thing about them is that you cannot actually stack them. You can't stack them to basically make the same thing, right? You can't what I'm saying is you can't confuse your right hand for your left hand if you're looking at it. It's very obvious because you have your palm on one side and then the back of your hand on the other. And so you can't just put your hands together and have the palm up and have your thumb projected in the same direction. Okay? Whereas socks, on the other hand, they are still mirror images of one another, but they are actually stackable. So we call that superimposable. And so since you can stack them, then those are superimposable mirror images, while our hands are non-superimposable mirror images of one another. All right, so in addition to being able to stack those socks, you can kind of think of it as like you can put them on either foot, right? Some socks might be very specific as to whether or not you should put them on your left and right foot. I have a pair, but I don't listen to it because don't tell me what to do. You know what I mean? Gloves, on the other hand, certain types of gloves, like gardening gloves, for example, are very hand specific. So you have to put the left on the left hand. And this idea of non-superimposable mirror images, like gloves, are basically what chirality is. So these gloves are said to be chiral, and our hands, also being non-superimposable mirror images of one another, are chiral as well. All right, and so again, hands are chiral. They are non-superimposable mirror images. All right, so since socks are actually kind of neutral, you can put them on either foot. They are superimposable mirror images of one another. Socks are said to be achiral. So we have these two words, chiral versus achiral, and chiral means that they are non-superimposable mirror images, and achiral means they are superimposable mirror images. And so, yeah, I mean, that's pretty much chirality in a nutshell. These are obviously more like tangible things that we're familiar with, but now we got to learn how to apply it to chemistry and organic molecules. All right, now before we kind of go over the nitty-gritty of actual organic molecules, let's give you a few more terms. And so chirality can also be discussed when we're talking about enantiomers. And so you're probably familiar with enantiomers already, you just don't know it. So amino acids, they can be broken down into two categories, or not just two categories, but in terms of three-dimensional structure, the L and the D in amino acid, right? Or L and D sugars. And so enantiomers are chiral compounds that are non-superimposable mirror images. Now, typically, they come in pairs. So enantiomers, if you have one mirror image, it's kind of like your left and right hand. A molecule is going to have a left-handed molecule and a right-handed molecule. So they usually come in pairs. And a carbon with 4 different groups is what we're looking for to identify an enantiomer. And then this is also known as a stereogenic center. Okay, so one important note to make is that when you have a compound that has 2 or more stereogenic centers, that molecule may or may not be a chiral compound. So for example, if you have 2 stereogenic centers, you still might have a compound that actually has a superimposable mirror image. And so that's going to bring us to the next kind of definition of chirality or enantiomers. The chiral compounds, they do not have symmetry. Okay, and so what we mean by this is it's going to take the form of a variety of things, and so we're going to have to go over that. But just remember, if a molecule is symmetrical, then it is not chiral, regardless if it has a stereogenic center. So let's take a look at the symmetry of this molecule, if it has it. Now, first let's point out that carbon in the gray color has 2 hydrogens that are white, a chlorine that's green, and a red bromine. Those are typical colors when you're talking about models of molecules. Now, does this molecule have symmetry? If we kind of move it around like this, and boom, let's pause it there for you. Now what we can do is kind of imagine slicing through this molecule with some beautiful red scissors and getting the same structure more or less on the left and the right side. So on the left, we would obviously have that hydrogen atom, as well as on the right. So there's the symmetry there. And then on the top, it might not be as obvious, but we would have half of a chlorine atom as well as half of a bromine atom as well. And this is okay when we're trying to figure out if the molecule has symmetry. We can indeed cut atoms in half. We can also cut along chemical bonds, just like we did. Now let's take a look at, that actually brings me to another point that's really important and perhaps confusing initially, but very easy after. Let's switch out this green chlorine with an oxygen, and then that oxygen will have a hydrogen on it. So if we wanted to orient this particular molecule in the same manner as before with the chlorine and bromine, kind of almost like they're eclipsed on one another, we can't, if we slice that in half, then what we would get is, at first glance, it doesn't look symmetrical because we would have that hydrogen from that OH on the left. But you have to remember that that CO single bond can actually freely rotate because it is a sigma bond. Now, when it rotates, that hydrogen is going to be projected upward at some point in the same plane as the one that we want to slice it. And so what happens is we would slice that hydrogen as well as that oxygen and the bromine in the back in half, and then we would get that's going to be our plane of symmetry. So we have to remember that we can rotate sigma bonds to allow us to create that symmetry or visualize that symmetry of the molecule. Okay, it might be difficult at first, but yeah, it just takes a little bit of practice. Now, switching out we're going back to the chlorine and the bromine. Now we have an iodine and a hydrogen on there. So now what we want to do is kind of look at this particular molecule and see if there's any symmetry. Now, any way you rotate it, try this with your modeling kit. Any way you rotate it, you can't slice and dice it to get the same thing on the left or the same thing on the right. It's just not possible, and that's the idea of identifying a chiral compound. A chiral compound does not have symmetry, and that stereogenic center needs to have 4 different groups on it, because this is going to be the first step in creating a non-superimposable mirror image. Now, the way symmetry kind of shows up in a 2-dimensional structure would be, for example, if we had this guy right here. This is propane, right? And now when we're talking about symmetry, well, we can actually see that if we slice this down right here, we have the same group on the left as we do on the right. And so that's kind of what we mean by symmetry. Okay, so that one's pretty straightforward. This one, however, it gets a little bit different once you start adding wedges and dashes and things like that. And so this might also look pretty obvious in terms of symmetry. If you cut straight down here, you have the same group on the left as you do on the right. Yep. All right, so now let's take a look at another one. Well, let me draw this guy right here, and then I'll also draw this one right here. Okay. Now, that's not supposed to be a wedge. It's just supposed to be a regular bond. Okay, so focusing on this cyclopropane compound, here's the thing now, if we were to slice it down here, what we have is, on the left side, we have a methyl sticking out at us, and then on the right side, we have a methyl pointed away from us. And so that's where these types of things get a little bit more tricky, because that's basically not going to be a plane of symmetry, because what we want to do is kind of create a mirror image. And if this particular methyl group is in the plane of the board or the screen, and this one over here is out of the plane of the screen, then those aren't going to be mirror images of one another. Okay, so but there is a different kind of a region, I guess, in terms of a plane of symmetry. That just means that we can't really slice the molecule in that particular spot. So let's erase all of these. What I mean is we can't really slice it down here. That's not the plane of symmetry, but there is a rotational plane of symmetry. So, that's going to be an inversion center. Okay, or it could be a center of symmetry. Center of symmetry. Okay, and these ones are a little bit more difficult to kind of see or visualize on paper. So go ahead and click the link in the upper right hand corner on the video, and there's a separate video that's gonna kind of it's basically me showing the symmetry of molecules with molecular models. Okay, so but more or less all you're really doing is rotating this molecule kind of about this plane right here, just basically flipping it over like a pancake. And if you do that, this particular methyl group is now projected in the back, and then this methyl group is projected in the front. And so it's basically the same look of molecule. Whereas if you flip this one, for example, what you're going to get is the methyl group's projected in the back, and so it's not necessarily going to look the same. Whereas this one, you can flip it 180 degrees over like a pancake, and it's going to look exactly the same with the wedge on the left and the dash on the right. And so that is your inversion center, and then so therefore it's going to have a plane of symmetry, and then it kind of makes things a little bit more complicated from there. If it wasn't obvious, that means that this guy is not chiral, right? And this is another way of saying that this molecule is achiral. And that's basically going to this point up above right here, where we say that with two or more stereogenic centers, a molecule may or may not be chiral. And so that is that carbon right there and that carbon right there are stereogenic centers. And the same thing for this as well as this, and this one just doesn't even have a stereogenic center, but so we already know that that's not going to be a chiral compound. But we're basically what I'm trying to point out to you is the idea that we do need a plane of symmetry in a molecule, and then we'll kind of go over how to identify stereogenic centers as well. But back to that cyclobutane. So if it was just a square, the cyclobutane, you can slice it that way, you can slice it that way, this way, or that way, right? So let's go back to this one, okay? Because that's seems to be it might be an option here. If you go there, you're slicing right through that. Now, at a glance, it looks like that is not going to be a perfectly sliced cyclobutane with the ethyl cyclobutane, because we have the terminal carbon sticking on one side and we don't have one on this side. However, you have to remember that, sorry, let me draw this a different way, that this particular methyl group, it can actually spin around, because remember, this is a sigma bond and you can rotate about that sigma bond. And so what you want to do is try and visualize the point at which this rotates and is actually at this point. So that would actually be projected into the plane of the board, right? And so if we drew that differently, if we actually gave it some, like a 3 dimensions, what we could do is place that there. We might do a hydrogen here and then a hydrogen here, right? So if we were going to slice it, we would slice in half. Well, now I feel like I need to do a blue line. If we were going to slice it, we would slice in half that basically along that carbon-carbon bond, and then we would leave a hydrogen on one side and a hydrogen on the other, and then we leave this portion on the left and the right. And so there's your plane of symmetry. It's just basically requires you to rotate about that bond and put basically not cut in between a bond, kind of like we did here when we can slice here in between the cyclobutane, but what you need to do is actually cut along the bond, and that's where the plane of symmetry lies. Okay, so again, if that doesn't make sense to you, check out the video link, and then that kind of popped up on the upper right of this particular video. Now, stereogenic centers, right? What are those all about? Really, again, the idea of An enantiomer and a stereogenic center is basically having a tetrahedral carbon that has 4 different groups on it. And so we can have sorry for the moving around of the screen, it's carbon with like a bunch of halogens on it, right? Just put all the halogens on it, right? So this particular carbon right here is a stereogenic center. So, sorry, that's not a Z. Stereogenic center. And typically what you'll see it'll be indicated with an asterisk, and that tells you that that is a stereogenic center or a chiral center. And the tricky thing about this is that what we're looking for is 4 different groups, right? And so here's the key phrase or word. It's groups. It's not atoms. Okay, so why that's important to distinguish is because let's say we had something like this, right? Well, bromine and chlorine are obviously different, but let's look at this particular carbon is the one in question, obviously, but we have a carbon bound over here, but we also have a carbon over here, right? And so what's that like? Those are so those are in fact the same atom, but if we look more closely, they don't belong to the same group. And what we mean by group is basically if you wanted to think of this is the carbon in question and the rest of them are substituents. This is an ethyl substituent and this is a propyl substituent. And so we have 1, 2, 3 group carbons coming off, and then on the other side we have 2 carbons coming off. And so these are 2 different groups, and therefore this carbon right here is stereogenic center. And I would refer to this as a chiral carbon, and we would draw an asterisk there to indicate that. And so this is what's tricky. You can literally have a carbon with a hydrogen, let's say a bromine, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on one side, and then a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11 on the other. And by definition, that is a stereogenic center because you have 4 different groups on it. Okay, and so you're going to have to count your carbons sometimes. Now, stereogenic centers are actually pervasive in the environment. They're all over the place. Like I mentioned before, the importance of chirality is it's basically the reason why we are alive, because our amino acids, they are chiral compounds, and they work in like left and right-handedness, and so all of our amino acids are L amino acids, and that's how our body functions with the L amino acids, but not the R amino acids, or the D as they would be referred to in biology. And so this is really important, and it poses a problem when making pharmaceutical drugs, because some of them may actually, the handedness of the molecule, amino acids, they don't work in our body if they are not the L amino acids, but some chiral drugs do still work, but they either don't have the same function, or maybe they don't work at all, or even worse is when they do have a function, it's not the same function, and it's actually a negative outcome. So, for example, thalidomide. So this is actually, or was, a drug that was used to treat morning sickness back in the day, and I think it was like in the 50s, maybe 60s as well, but it was viewed to be harmless. I mean, this is why we have drug regulations now, right? It might seem kind of annoying, but they are important because they do help us and keep us safe, because if we had a little some sort of regulation on this particular drug, then we wouldn't have had the issues that we had back in the 50s and 60s. And so what happens here is, well, first I really want you to kind of think about where the chiral carbon is, or the stereogenic center. And I'll point it out in a second. One of the key things to look for whenever you're trying to figure out where that carbon of interest is, that stereogenic center, is you always look at the wedges and the dashes. If there's a wedge and a dash, then they put that there for a reason, because it's probably going to indicate some sort of stereochemistry. And so this one right here is, we'll explain what this means, but this would be the S configuration, and this is considered the R configuration. And so thalidomide actually has 2 enantiomers. Okay, so 2 enantiomers, and one of them is good for morning sickness, and the other actually causes detrimental side effects to unborn children. So they just, unfortunately, the women that were taking it were taking it because they had morning sickness due to the pregnancy, and so it caused birth defects. One of them, again, only is the cause of the birth defects, while the other was the drug that helped kind of alleviate that morning sickness. But without the regulations, it was not. Unfortunately, that was just kind of something we had to do, or that happened, and we learned the hard. I mean, we can talk all day about this, but I just kind of wanted to point that out. Again, just I like to point out the importance of the topic, of course, but then also throw some interesting facts out there. So the other idea about stereogenic centers is that you can have more than one, as kind of mentioned above, and especially pointing out the symmetry. So we can have a lot of naturally occurring substances have more than one stereogenic center. So this one right here, for example, this is ephedrine. So ephedrine. And I want you to think about where that chiral center is, or that stereogenic center. This guy right here. Ooh. Mind of its own, I tell you what. Let's see. Lots of OHs. What do you think this is going to be? If it's got lots of OHs, it's probably going to be a sugar, and it's fructose. Okay. And so let's look at the number of chiral centers. So first of all, this was a stereogenic center. That was a stereogenic center. We had 4 different groups on it. Now what we want to do is look for carbons with more than, with 4 different groups. And this one right here, if you said that one, you were correct, as well as this one right here. Those 2 are the stereogenic centers in ephedrine, as well as this one, and this one. Okay, this one is not on the end because that carbon has 2 hydrogens, which are the same substituent, and we need 4 different ones, remember. All right, so drawing pairs of enantiomers, drawing pairs of enantiomers. This is, I don't know, it's a skill, something you definitely need to practice on, but I think it's really easy to acquire. And so first what you want to do is try and figure out where the stereogenic center might be, right? And so let's say we had a bunch of compounds that may or may not have a stereogenic center. They probably do, since I'm drawing them, and that's the point of this particular discussion, but hey, you never know. So you can pause the video and then try and figure that out first, or because I'm going to move on. But let's go ahead and label those. This guy's, so remember, anytime you have CH2s or CH3, you definitely want to just skip those. And so that leads me to here, which is in fact a stereogenic center. And now what you want to do in order to draw the enantiomers is basically draw it out in the form of wedges and dashes. Okay, so this guy will go to this, and then you can just draw that chlorine as whatever you want, either a wedge or a dash, and then you can draw the hydrogen that's in the back with the opposite thing. And then it's really easy, actually, straightforward drawing this particular one, because all you have to do now is draw the same thing again, but instead of having the chlorine as the wedge, you just swap it with the hydrogen, and then the chlorine goes to the back. Okay, now you could also, here, let me move these guys. Let's see, you could also draw it like this. So we have this chlorine and this hydrogen. Now imagine this is a mirror, and basically enantiomers are mirror images of one another. Okay, so mirror image is what we really want. And how would we draw that? Well, first I would personally draw this portion, and so you go down, and then instead of going this direction, you bring it back. Okay, so that's the beginning of that mirror image. This is the chlorine. Notice the chlorine is coming towards the other chlorine, but it also has that wedge, and then we have the dash in the back with the hydrogen. Now hopefully you can kind of visualize how those are mirror images of one another. And this is just another way of doing it. And because I know typically you'll see things in this kind of format where you'll have the wedges and the dashes with the bonds that are in the plane going kind of projected up into one side. And so this is also a very helpful way to draw the enantiomers, just kind of visualizing a mirror there and then drawing the mirror image, drawing everything opposite. But for me personally, sometimes you can just draw it like that. It's really straightforward in my opinion. Okay, so let's see what this one looks like. We've got here, and now we've got the OH, and now we're able to just draw the hydrogen in the back. We also have the hydrogen and then the OH in the back. So let's see, again, very straightforward. Let's draw the sulfur, and notice I'm keeping the less crazy groups in the plane of the board, because those are, rather than drawing the wedges and the dashes with those groups. And so we draw our wedge and a dash here, and then we just put our NH2 on one of them and then our hydrogen on the other. And then we've got one enantiomer drawn. Now we've got our other setup. We'll put a hydrogen in the front now, and then we'll put our NH2 there. Super easy, right? Again, it might take a little bit of practice depending on the structure of the molecule, but there you go. And it's definitely going to be interesting maybe if you have more complicated structures with more than one stereogenic center, but just take it when you get it, and just give it a try. You can apply either method, either the mirror image, or just taking the Stereogenic Center and swapping it. So that's going to be it for now on this particular topic. I will check out the next video on basically RNS configuration. That's assigning like amino acids would be like L and D, but when we're talking about organic chemistry structures, we assign RNS configuration. And then we have a little bit of nomenclature along with that, but then in addition to that, we'll introduce diastereomers as well as meso compounds, and also the cyclic structures and how to kind of determine if those are chiral as well. So check that out on the next video, and also make sure you check out the video on the molecular symmetry with the modeling kit. If you can't visualize it in on this format, the two-dimensional drawing of structures, the modeling kit might help.